So let's talk about one of the most interesting subjects in mathematics, trigonometry. So trigonometry is pretty much a subject that is taught across schools, colleges, engineering diploma, engineering degrees. I think it's taught across all the facets of the education system. And sometimes the topic can be very overwhelming to know what the heck we are talking about. Where are we even using it? Are we even using it? And just students are always confused that why am I even studying this? What should I do with this? So I thought that let me just make it more fun and just let me give you a spin on the story. And like anything and everything in the world of teaching, if you understand the rationale behind the history of a topic, why did we study that, how did it evolve, and some interesting facts and trivias around that one, that makes the subject very interesting. So I thought let me just spin some quick story, interesting facts that I kind of gathered on the internet and just try to package into a story and give it to you guys. So if I do this as a precursor to help you start studying trigonometry, I thought it will be fun. So with that, let's get started on trigonometry. So at a high level, what is trigonometry? Going by the definition, right? So going by the definition, trigonometry is a Greek word, and what it stands for is a trig is anything that has a triangular shape. That is what is trig, and metry is measurement. So what is trigonometry? Is measuring the different dimensions of the triangle. It could be the angles or it could be the lengths. So that's what trigonometry is all about. So measuring the different dimensions of triangle. That's what trigonometry is all about. And any student, if you ask any student, what do you know about trigonometry? I'm not sure if they know the meaning of the word, but there are a couple of things that the student might say that, okay, in the context of trigonometry, what do they remember? What are the things that comes to your mind when you say trigonometry? So regardless of what is the depth and the breadth of the understanding of the student, the two things that come to a student's mind will be Pythagoras theorem, which is a square. If you take this triangle, right angle triangle, and if I name the sides of the triangle as ABC, with C being the hypotenuse, then a square plus b square is equal to c square. That is what is the Pythagoras theorem all about, and Pythagoras was a Greek mathematician. And the other thing that comes to mind is sine theta and cos theta. That's what they know. Okay, there's something called as theta, which is the angle, and we know something called as sine and something called as cos. And this whole play of sine and cos is what defines most of the engineering and applied mathematics, right from your Fourier series or Laplace or integration, your applied trigonometry to your physics, and everything just is driven on the fundamentals of sine and cos. So if you understand where did this sine and cos come from, maybe you'll be able to appreciate and just understand that, okay, everything that evolved over a period of time is not only interesting, but it's fascinating, and the fascination comes when it comes from different parts of the world. And that's what we're going to learn today, a bit of trigonometry on what's going on and stuff like that. And if you see here, I've also drawn a circle. So another thing about trigonometry, when you talk to students, what does it come to mind apart from your Pythagoras theorem? They might say that, okay, we understand there is a circle and there is a radius and there is this base and this angle theta, and everything about the measurement of angle theta we can apply some trigonometry, and that's all they know. So this is called as the unit circle. So that's another thing that comes to the mind. And if you see, as I said, Pythagoras was a Greek mathematician. The sine and cos, the words are Latin. They are derived from the Latin. They have the Latin roots of if you go by the literature. And who kind of came up with the concept of trigonometry? So if you just check out the history and the Wikipedia and stuff like that, there's another Greek mathematician by the gentleman named Hipparchus. So Hipparchus was known as the father of the trigonometry, and a lot of credit goes to him because he built some literature around that one, and he formulated a lot of stuff on trigonometry and how to use that. And that's kind of the history of trigonometry. So if you see here, what is very unique is the word trigonometry is Greek. The two of the mathematicians out of the many who were involved in the concept of trigonometry are Pythagoras and Hipparchus, more like geometry and trigonometry, because the right angle triangle concept is more geometry. The word sine and cos itself comes from Latin. So we have this fact. So what is so interesting about it? What is so interesting? The mind-blowing fact of this whole thing is the word sine and the cosine, which we just study blindly every time, and it is so sometimes interesting, intriguing, at the same time it could be overwhelming. It has come from India. It has got its heritage from the Indian literature. That's the most beautiful thing about this, that it's not the Greeks who invented the sine and the cosine. It is the Indians who invented that. But you might argue, but you're saying that the word itself comes from Latin. So how does it matter, or how does it even prove that it comes from India? What is the connection? And this video is all about connecting the dots and giving a bit of history and taking you through the journey of how the sine function got its name, and hence the cosine function. So with that, let me take you way back in the ancient history of the mathematics scale that I've put. Sorry for my doodle here, but I think I'll be able to explain you. So if you take the time scale, I'm going to fast forward some of the things because I want to come to the point right away. So if you take the history, right, and put it in a time scale, so maths was being evolved everywhere, but we should know what are the civilizations and who are the maths geniuses who are doing different things in a different time scale. So if you see here, the blue line here is my time scale, and I've put 0 in the center, which is pretty much to have a demarcation what is the before the common era, the BCE, and what is the common era, in other words before Christ and during and after Christ. So I'm just using the common era terminology. So anything beyond 0 is in super ancient, and anything 0 towards on the right side is pretty much going into the common era of that. So if you see, I've plotted the time scale from 2000 years and beyond, and going forward 2000 years. So that's what the time scale is all about. And if you see the major contributions coming from different civilizations during the ancient times around the 2000 years were primarily contributed by the Egyptian and the Babylonian, who had the major involvement in defining geometry. There were some things going on on the Chinese side, and there was something going on the Indus Valley, which is pretty much Indians. So this bunch of folks in the ancient times were doing different things about mathematics and trying to put up with some stuff that we are using in the modern day mathematics. But the Egyptian and the Babylonian have significant importance because they were primarily responsible for the application of geometry, or rather using geometry to do things. And history speaks for itself. If you see Egyptian, the way the pyramids have been built, everything has to be built in a certain angle, and everything does have a kind of a right angle to its shape, and they are like huge and astronomical in terms of size. So that talks about during the ancient times, which is more than 2000 years BC or beyond, they were using kind of a geometry to build that. They were using, and back then it was not more about the applied geometry. It was basically to do getting different shapes of geometry and trying to do a play on that one and use that for kind of building whatever structures they need to build. It could be pyramids, or it could be water canals, or it could be temples. The Babylonians were building magnificent temples of humongous size using these different shapes of geometry. And that's where the geometry kind of was born, if you see the ancient part of that. And the primitive shapes of geometry that they were using were circles, squares, and rectangles to build stuff like that. So that's what was happening in the ancient history of 2000 years and beyond. And if you fast forward on the time scale, anywhere between, let's say, all these numbers are I put, but it's not accurate, but that's not the point here. But if you see anywhere between 600 BC to, let's say, 500 AD, that area of the timeline, a lot of things happen. Okay, one of the things that happen, if you see the green text that I put, is the evolution of Greek mathematicians, or how they evolved. And there are tons of, if you go to the history, there's tons of Greek mathematicians, but today I've just put a couple of names of Pythagoras, like I just said, and Hippocrates, because he's the father of the trigonometry. So Pythagoras came in play sometime around the 600 BC, where he came with this Pythagoras theorem. And the beauty is, the Egyptian and Babylon already were doing things regarding geometry way before the Greeks even started. But the Greek mathematician, what kind of contribution they made is, the folks in the previous side, Egyptian and Babylonian, they were trying to just apply geometry to get what they needed, and it was all relative in terms of understanding the shape and how it functions. And as long as they can measure something, whether it's a temple or it's a canal or it's a pyramid that they're building or a length of an agriculture farm, they're okay with that. But there was no logical reasoning, there was no structured way to do that, there were no formulas, there were no logical reasoning and deducing something from the facts and making it more standard and stuff like that. And that's where the Greeks come in. What they did is they took all the work that was existing on the geometry side, and they started applying rules to that. They started proving theorems why certain things are working and all those things, and started packaging those, which was used further downstream across the different parts of the world. And that's their significance, like taking what is existing and packaging into more structured way. That's where they were coming in, and that's where they published a lot of literature. And a classic example of that was, if you see the Pythagoras theorem that we talked about, here is a triangle, right? Let me take this picture over here. So here is a triangle, right angle triangle, and there are three sides, like I said, A, B, and C. And the Pythagoras theorem says the formula is a square plus b square is equal to c square, right? That's what the formula is, and c being the hypotenuse. And this is the formula they gave. But where did this have its origins from? Where did they get this idea? Where did they get this critical thinking? And that has origin into the ancient maths of Babylon and the Egyptian, where they're building pyramids and temples, where they're doing a lot of geometry stuff. And the way it was structured is, they already know, the Babylonians and the Egyptians, they already know that the equation is true because they were using it in the calculation. But they had never written this formula in that per se and formulated that. The way they were using is, if there is a triangle, and if you use each side of the triangle to build a square, like I have built, I have taken the side of A and I have built a square around that, and the length of all the squares are similar. The diagram does not show that, but assume that's a square. Same way, if I go to the hypotenuse C and I build a square around that, and similarly I go to the base B and I build a square around that one. So what the geometry the Egyptians and the Babylonians kind of used in terms of calculation is the sum of this square, and actually it's literally the square box, the sum of the square box of this and these two squares is equal to the sum of the third square. So the common notation where you think that this is a square, it pretty much has history that it was an actual square box that they were using, and they were using that, but they never formulated that. They were just trying to use that, okay, this is how I need to design, and this equation might be true, because if I want to find what kind of square box I need to put here on this dimension, all I need to know is what is the area of this square, which is a square, and what is the area of this square, b square. And if I design a square which is equal to the area of c square, I can mount that square on this ramp, which is where they were using geometry to build a lot of construction activities, and that's where they're using. And Pythagoras took that kind of theory and tried to formulate, saying that, hey, this is not only for the geometry, it can be used for further this thing. And he kind of applied some logic and deduced this mathematical formula that a square plus b square is equal to c square. And that's how the Greek that is an example of how Greeks were trying to formulate everything that they had, or they were borrowing from, or being influenced from the previous mathematicians in Egypt and Babylon. So that's kind of the history stuff going on. And now let's move forward to the time scale of what we were doing and what kind of things that we were doing. So if you take the Indian mathematics, India has one of the most ancient civilization, and like I mentioned here, they were already doing some stuff here, and we were doing all throughout the way. In different areas. We already had a number system where we pretty much use the decimal number system, which is what the world is adopting today, 1 to 9 and stuff like that. But if you take the Indian history of mathematics in the context of trigonometry and what we use, a lot of interesting things happen in this particular zone, the 250 and the 500 AD common era. And I've kind of plotted the stuff here on what's going on. I've just taken that time scale for Indian and plotting. So one of the major use case in the ancient world was to construct things, whether measuring or fencing around the agriculture farmland, or building a temple, or building a pyramid. But as the world evolved and as trigonometry was formulated by Greeks, a lot of interest was being generated across the world, across the board of different mathematicians in different geographies: India, China, Egyptian, Greeks, primarily Greeks in India, where they're trying to use trigonometry into calculating or into the world of astronomy, where they wanted to know and learn more about the sun, the moon, the planets, how they are structured, what is the angle, what is the distance between each of them, and stuff like that. And they're trying to use a lot of trigonometry into astronomy, and that kind of explains how kind of it evolved. One of the most classic examples of trigonometry back then and even back today is astronomy. What is the different angle, and they pretty much kind of derived a lot of stuff, the distance between the earth and the sun, or the moon and the earth. Pretty much they had a lot of distance fairly accurate in those days, just using this basic applying basic trigonometry to different planetary positions and stuff like that. So so moving forward, the Gupta period is something where you had all this folks from the ancient history who were pretty active in the 250 and 500 AD, and that's where a lot of applications of trigonometry into astronomy came in picture, like I said. And if you see here, just to give you a preview of the different empires so that you don't forget the time scale. So if you see here, this is your Egypt that I talked about in the ancient past, and this is your Babylon and Mesopotamia, which in the modern day is Iraq. And then you have Persians, which in modern day is Iran. And if you see here, we are here, the India. Oh, sorry about that. And then we have Chinese here, the same stuff, Arabians and Persians here. So that's how the map looks like in the ancient world. And so what was happening in that time frame is there were a lot of Vedic mathematics, or the Siddhantas, that were getting applied for calculating trigonometry and different rules. And we were always active, like as Indians, we were always active in from the ancient history of 2000 years and beyond, and coming fast forward to 250 AD. And during the Gupta period, a lot of Siddhantas were formulated into different formulas. And all our ancient mathematicians who came in those period, primarily Aryabhatta, kind of applied those Siddhantas in kind of some sort of formulas, and a lot of knowledge was being distributed back and forth into this world of mathematics between Greeks and between Persia, between Arabic, and between India and Europe, stuff like that. But this was a time scale on when each one was active and stuff like that. And after the Indians, if you see the Arabic world or the Islam world, which I combined both Arabic and the Persians, which is the Iraq and Iran kind of map that I showed you, they were also getting active in this zone. Let me use a different color. Hold on. They're also getting used into this zone. So what they were trying to do is they were trying to take a lot of literature that came in from the Indian continent and that came from the Greek, and trying to understand. And they also had a lot of intellectuals from their side, mathematicians who have invented a lot of stuff, but they're trying to just borrow the text into the local language and trying to convert that and then apply their own stuff and build things. So a lot of knowledge was getting exchanged back and forth. And if you see, the Arabs were primarily responsible for translating and relaying back the literature to Europe, which came much later into the historical part, somewhere around 12,000 AD and later, where they were started to use maths, and they were trying to standardize it across the world. And from there it went to the Western world, where what we know as in today's world of modern mathematics. So that was kind of the thing that was going on everywhere in the world. And like I said, we have our ancient mathematicians, Aryabhatta, Bhaskara 1 and 2 and stuff like that. But today let's focus on what happened between the Siddhantas and Aryabhatta. Between that period, during the Gupta period, the trigonometry that we know today, that we study in modern day school and early colleges, that is where it evolved, and that is where I'm coming to what happened to how things happen. So if you go here, if you see here, I was talking about how the Arabs were the mediator between converting the math script and taking what they have, applying it, and then pushing it further to Europe, which was and Latin was the language of the Europe, and then it got converted into English in the Western world. So that's what was happening. But how did the sign come up, and what happened there? What is the history of that? When I say that it came from India, and which is very mind-blowing and intriguing, is as follows. If you just take this time scale of this particular section here, just here and here, the Greek and the Indian stuff, just this portion that I'm talking about, I'm boxing it here. So what was happening is the Greeks were doing their own stuff and the Indians were doing their own stuff, okay? And by this time, geometry and application of trigonometry was already prevalent. And what the Greek were trying to do is they were trying to apply the Greek geometry. Sorry, Indians were trying to apply the Greek geometry. But what the Greeks were trying to do is they were taking a circle and they were trying to do a lot of things for the astronomical things. As I said, they want to do just study astronomy. So what they were trying to do is they were taking a circle and they were just using these two arms and subtending an angle theta, and this portion is the chord which connects the 2 points on the circle with the radius r. So they were just trying to see if they can get the value of this particular thing that I have highlighted, and this is a full circle and this is a full chord, and they did get something going on that side, but it was very rudimentary and very difficult to do that, and they were trying to figure that out. And what the Indians were doing on the borrowed geometries, they come like a combination of borrowed geometry from here and the Siddhantas, like I told, and they're also using the same use case. They were trying to study astronomy and what's going on in the planetary positions. So what they did, very, very interesting and very, very intriguing, is they did not take the concept of full circle. They said, I don't want to have the measurement of the full chord. I know that that's important, I need that. But if I divide this into half like this, which is what here is, and just try to measure this base here with the same angle and the radius r. What if I do that? And they used to have that logic, and for some reason the half angle and the half chord logic worked out because they were able to calculate, and they started defining a table that we use today in terms of sine and cos. How were they defined? The earlier tables were exactly not the same, but the origin of the table comes from there, where they started publishing the values, and that kind of translated and transferred and traveled everywhere around the world. But what has that to do with the name sine and cos? And that's where I'm trying to come in my last 2 minutes. So if you see this portion of the half angle and the half chord, and if you just take this area that I'm highlighting here, okay, this kind of looks like this. This is a circle radius r, this is the base r, and this is the half chord, and this is the arc of the circle. So if you just take this portion, right, it looks like a bowstring, okay? So this is the string, this is a string, and this portion is called as the bowstring because that's how it looks like. If you have seen in the ancient past Ramayana and Mahabharata, you would have known. And this is the angle theta. So when they applied this and they're trying to formulate a table, something interesting happened. So this is where we'll come into the final part. So this bowstring that I'm talking about, this portion, the line that is called as the bowstring, right? The bowstring in Sanskrit was called as ja. I might be pronouncing it wrong, but you can understand appreciate the gravity of that, what I'm trying to come here. Ja, or it was also called as jiva, J-I-V-A in Sanskrit. When the Arabs were trying to borrow the literature and translating it, they were trying to do it in literal sense, not in the mathematical sense. Okay, whatever words you have, let me transfer what it means into my world and let me transfer it literally. And that's where this jiva, the equivalent of jiva for them, become jib in just terms of combination of alphabets, and jib. And normally the way the Arab script is structured, they don't use any vowels or lot of alphabets they need to have to form a word. So, and they use a lot of abbreviations, and they pretty much understand what each abbreviation stands for, right? So this jib was abbreviated and it became jib, JB in the Arabic world. And what happened was, like I said, a lot of things were moving from the Arabs to the Latin world. So when this kind of literature moved further, and they were trying to transfer into the Latin literature in the Roman Empire or in the European world, they took this JB, and without knowing or understanding where this came from, they started using the Latin equivalents of what this possibly could mean, and they mistook this JB or jib as an abbreviation of an Arabic word called as JAYB, and which in the Arabic world means to fold or to have a cavity kind of thing. So they thought that's what this JB would stand for, and they said, okay, a cavity or fold in Latin translates to sinus, and that's where the sinus word comes from. It's a wrongly constructed translation of JAYB without understanding the context and the history, and a literal translation of Latin to the word fold or cavity that I'm talking about here. That's what it means. And when this Latin world was moved into further into the Western world, in the today's world, the sinus becomes sine. So that's the history of the word sine. It does not mean anything. It's just a wrong translation of the word jiva, which was an Indian invention and an Indian world of tables. When it moved across the world, across the different time scale back and forth, it was misconstrued as sine. And similarly, the cosine aspect of that, right? The Indians were using this part, like I said, if this is the sine part, this part which is adjacent, they were calling it in Sanskrit as koti jiva, ko, and that also got poorly translated into cosine. So this what is sine and cosine, and it's not only this for sine and cosine. There are zillion words which has got wrong translation. One of the interesting was khanda. Khanda is basically a sugar cube like we use today, right? And that got translated into candy. Similarly, even algorithm that we know in modern mathematics has some origin to do with the way Indians did compute the maths. There was a word algorithm which is not an Indian word, but this itself was computed from some other Indian context, and it was literally transferred into that. So even this word has got Indian origin, this word has got Indian origin, and so is sine and cosine, which we are going to study in future videos. I hope you guys enjoyed the history of sine and cosine and would be appreciating of how we can use this in today's world to do a lot of things. More on my other videos.